Hi, thanks for joining me today. I'm going to be going over problem 1 from week 4 of the Invariants Summer Puzzle Competition. As always, I'll leave a link in the description below for the Facebook page of the Invariants, where you can find out more details about the competition. This is the problem we have for today. We have a closed interval I, which is a subset of the reals, and two functions f and g from I to the reals, both of which are non-zero on this interval I. We then define the norm of f, and this norm depends on g and on some positive integer m. We define the norm of f to be equal to the integral over I of the magnitude of g times f to the power of m, and then that integral there raised to the power of 1 over m. So the mth root of the integral of the absolute value of g times f to the power of m. We now also assume that f and g are continuous. We want to prove that the limit as m goes to infinity of the norm of f exists and doesn't depend on g. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the way we're going to solve this is by using a few different tricks from analysis. The first one we want to use is the integral mean value theorem. So remember what f, or the norm of f, was, or I think it was written the other way around, doesn't really matter, it's just notation. It's given by the integral over I of the absolute value of f to the m times g, take that guy there and raise it to the power of 1 over m. Now, what's quite nice about this is that our integrand is nice and non-negative. In fact, it's strictly positive because remember f and g are not zero, and therefore their magnitudes will be strictly positive. And because we're assuming they're continuous as well, that means the magnitude of f and the magnitude of g are also continuous positive functions, which is super nice for analysis. It means we have lots of tools we can use on them, and what we're going to use, as I say, is the integral mean value theorem, which says that we can kind of strip out a value of g and take it to the front of the integral. So what does that mean in maths terms? There exists some number xi which will be in the interval I, but this number xi will also depend on m, but that's fine. There'll exist some xi m in the interval I, such that this guy here is actually just equal to, and now I'm going to factor out, or kind of strip out this value of g from the integral, and then multiply by I, f of m, and then of course we've still got this 1 over m, in the exponent here. So this is just a direct result from the integral mean value theorem. Have a look at what that is if you've not seen this before. But let's continue. We have this guy here, and now, well, we've got this g of xi there, and we don't know what xi is. All we know is in I. But remember, I is a closed bounded interval on the real line, so we can use the fact that, well, because it's closed and bounded, then and g is a continuous function on I, it's going to be bounded as well. And it's also going to attain its bounds. And for now, we don't actually need to know that g attains its bounds, just that it's bounded. And of course, because g is positive, the magnitude of g is, because g is never zero, the magnitude of g is going to be strictly positive. So there are some numbers, little c and big C, such that this inequality holds for all values of x in I. So we have this thing here. So of course we know that g of xi, or sorry, I should put absolute values here, and then I can put a 0 here. And so we know that g of xi is going to be somewhere in this interval, c. So this thing here is, on one hand, it's going to be less than or equal to c to the 1 over m times the integral, c to the 1 over m times the integral on I of f of m, and then that guy there to the 1 over m. And on the other hand, it's going to be bigger than little c to the power of 1 over m of the integral of I of f of m, raise that to the 1 over m, like so. So this guy here, we've already kind of bounded it, but we want to do a little bit better. So let's have a think about how we can improve this. Well, firstly, we also know that f is a continuous function on I being a closed bounded interval, so it's going to attain its bound, and this is important, and this is a result from analysis. It's going to attain its bound, which means there exists some number, we'll call it x0, in I, such that f of x or the magnitude of f of x, attains its bound at x0. So in other words, f of x is less than or equal to f of x0 for all x in I. Why is this important? Well, I'm going to claim that this norm here that we're considering, is actually just equal to f of x0. And in fact, this is what's known as the sup norm, which you may have seen before if you've looked at norms before, but just the maximum value that f can, or the magnitude of f can take in this interval. Well, let's prove this. Well, let's firstly prove that this thing here is, or what I should say is the limit here. That's my claim. So what I'm going to firstly do is prove that this guy here is always less than or equal to the sup norm. So it's always less than or equal to f of x0. And this is actually pretty straightforward. If we look at this inequality we have up here, we have that the norm of f and is less than or equal to c to the 1 over m times this integral here. But this integral we can also bound because we know that f is less than or equal to the magnitude of f of x0 on its interval. So this is going to be less than or equal to the integral on I of just the constant f of x0 raised to the power of m, then that guy there to the power of 1 over m. But of course we're integrating a constant, so that's just going to factor out, and I'll be left with this is equal to c to the 1 over m times the length of I, which I'm going to denote with this, to the power of 1 over n times f of x0, like so. So I get that this thing here, this fmg, is less than or equal to this thing here, and then if I take the limit as m goes to infinity of both sides, I get that this thing here is going to be less than or equal to the limit as m goes to infinity on this side. Remember, big C is a positive number, so when I take it to the 1 over m, that's going to tend to 1. Similarly, I has positive length, so that's a positive number raised to the power of 1 over m. That's going to tend to 1, so this tends to 1, this tends to 1. This is a constant with respect to m, so this is going to be less than or equal to f of x0, which is exactly this sup norm sort of thing. So we've proved that this guy here is less than or equal to this thing here. We now need to prove that this guy here is also bigger than or equal to this thing here. But let me clean up my screen and we'll move on to that. Okay, so all we have to do now is prove this guy here, that the limit as m goes to infinity of the norm of f is at least the sup norm of f. So the way we're going to do this is, again, by using kind of a standard trick in analysis. We know that f is a continuous function and it attains its bound at x0. So in particular, we know that around x0, f is going to be pretty big, or the magnitude of f is going to be pretty big. So let's put this in maths terms. Let's choose some value of epsilon. So firstly, we know that f is never 0, so that means the magnitude of f is strictly positive. So that means that the magnitude of f is bigger than, let's call it c tilde, bigger than or equal to c tilde, and that guy there is 0. So what we're going to do is just let epsilon be some positive number between 0 and c tilde. Cool. Now what we're going to do is a very standard epsilon delta argument. Let delta be such that the interval I delta, which I'm going to define as x0 minus delta, x0 plus delta, but of course we've got to make sure we stay in the interval I. So this is how we're defining I delta. So delta is chosen based on epsilon such that this interval here has the property that for all x in I delta, the magnitude of f of x is bigger than f of x0 minus epsilon. So again, this is just a standard fact of this being continuous, and we're attaining our upper bound at x0 and that sort of stuff. So go through this in a bit more detail if you have to, but this is all just standard epsilon delta stuff. Cool, so that means that the magnitude of f of x is big in this interval here. Let's go back to what we have up here. Let's look at the norm of f. We know that this is bigger than or equal to little c to the 1 over m from before, times the integral on I of f to the m raised to the power of 1 over m. Cool, but this is obviously going to be bigger than or equal to this little c to the 1 over m times, keep everything the same except this I I'm going to change to I delta of f of m to the power of 1 over m. Cool, so basically I've just made this interval here, I, smaller, bring it down to I delta, but now we know that on I delta, f is bigger than this constant here, f of x naught minus epsilon. So we can actually say, replace this f to the m with f of x naught minus epsilon to the m, and because that's a constant, factor it out of the integral. So this is in fact bigger than or equal to little c to the 1 over m times the length of the interval, which is I delta, raised to the power of 1 over m, times this guy here, which is bigger than or equal to this thing to the m, and then take this 1 over m, so it's just f of x naught minus epsilon. So the norm of f is bigger than or equal to this thing here, and again we're just going to take limits as m goes to infinity. So on the left hand side we get the limit as m goes to infinity of the norm of f. I always get these m's and g's mixed up. This thing here has to be bigger than or equal to the limit as m goes to infinity of this thing here. C is a positive number, so this thing here turns to 1. Similarly, I delta, the length of I delta is positive because this is clearly a positive, it's a positive number, and it intersects with I. It's all going to be nice and positive. So this is a strictly positive number. Raise it to the power of m, it's going to tend to 1. So 1 times this thing here, and this guy here is independent of m. So this is bigger than or equal to f of x naught minus epsilon. So we get the limit as m goes to infinity of the norm of f is bigger than or equal to the sup of f minus epsilon. But of course, this epsilon we're free to choose in this interval here, 0 c tilde, so we can make it arbitrarily small, make it as close to 0 as we possibly can. And because this thing here is true for all epsilon, it must follow that it's true for every single epsilon, and therefore it must be that this thing here is bigger than this thing here. So I'll just put that over here. Therefore, the norm that we have, the limit as m goes to infinity of this guy here must be bigger than or equal to the sup norm of f. And that concludes the proof, or proving that this guy here is in fact equivalent to the sup norm, because we show that it's bigger than or equal to and also less than or equal to the sup norm, and thus must be exactly the sup norm, and it clearly is independent of g, which is quite nice. So that solves the problem, and a lovely extension task which I encourage you to have a go at is, does this result necessarily hold true if we drop the condition about f and g being continuous? So if we no longer insist that f and g are continuous, what happens to the problem? Is it true that this limit must necessarily exist? If it does it depend on g anymore? All these sorts of questions you can ask. So do have a go at that extension and let me know your thoughts in the comments. And if you are stuck with that, hopefully someone will post a solution or give you some hints in the comments as well. Anyway, thank you for watching. Do have a good look at some of my other solution videos as well. This is the first video I've made where I haven't got a whiteboard in the background, and I'm doing the maths on kind of a virtual whiteboard. So let me know what you think about that as well. And also, if you're new to the channel, please do consider subscribing, liking the video, commenting, and all that sort of stuff helps with the algorithm shebang. So that's always useful for me. It's all free for you. So yeah, it's a win-win. Anyway, I'm going to stop waffling now. Thank you for watching, and I'll catch you in the next one. Have a great day.